Let's see how that works. All right, guys. So let's come back to hey. Number why we're here to see who's wearing green. Not many. Shit. All right. I am wearing green, just can't see. Doesn't count. No. That's right. You're always ready for. That's right. Gingers are always ready for St. Patrick's Day. No. All right. So before we get. Before we get into any questions from homework? Yes.
Okay, 11.1. I had I don't remember what number it is. I just know the numbers that they gave me. It was like n squared, or no, it was n plus 1 over 25n plus 1, but all that was under a radical.
That was from the book or from the?
That was online.
All right. So tell me.
25 was changed.
Something like that.
Yeah, and I wanted to know if it was converted. I think it's number 30.
It's related to number 30 because this does. Yeah. Okay. Good. So it's related to number 30 in the textbook. And this is asking if this converges, the sequence.
Yes.
Because 11.1 is all about sequences, and the minute you learn about series, you start doing that to the 11.1 shit. You're all confused. Sequences are always easier to work with because there's less going on. There's distinct elements of a list. Right? So that's easy. So how do you determine if this is going to converge or not?
You don't even know. It's just you just take the power away.
That's scary. So I mean, no. So first, tell me what it is. Why would you do L'Hopital's? Because you have to take a. No. When does L'Hopital's work? When you have a
Indefinite.
limit. So see if this converges. You take the limit. Let's start there. You guys remember this rule of limits? I mean, watch this. You guys do this automatically. Let me give you a simple one. What's this? Oh, that's good, Jeff. That's a simple one. What's that? Don't make. Yeah. What is it?
5.
Easy shit, right? Why were you able to take the limit inside the radical? Because the radical is what kind of a function? You can take limits. We always forget the beginning of a theorem or a process. There's always this. Given a function that is continuous or given a function that is decreasing, or these are going to become very important very soon. You got to know when you're allowed to do things. So very often the function's got to be continuous, and that's exactly what's happening here. If the function's continuous, you can just bring the limit inside. Hallelujah. So then this equals square root of what happens inside? Just check. What happens in there? The same degree.
Yeah.
Okay, done. Yeah. Simple shit. Simple, easy shit. Right. Just don't forget that. It's all. You just bring the limit inside and attack it. It's just a ratio of polynomials. Then inside of a radical, that just square roots the end result.
Okay. I tried to put in 1 over 25 because I thought you just take the radical and put it as power, but that's obviously...
You could. L'Hopital's would be so desperately disgusting because they would just continuously do this. Flip. Because when you take the derivative of something to the 1/2, you end up with a negative 1/2 power, which would flip. So they would both end up, they would flip and then they'd flip again. You get all this accumulated shit outside. Continuously getting worse and worse. Right? And you're like, damn you, L'Hopital. No, but it's not L'Hopital's fault. You don't want to do that here. Is that cool?
Yeah.
Don't make more of that than it is. So it's fundamentally a rational expression inside of a radical, but the limit doesn't care about the radical. It just jumps inside of it. All right. Good question. Anything else from homework? Yeah.
40, 11.1.
Ooh, yeah. All right. What does this look like? graphically before I get a smartest answer?
Asymptotes.
Yeah, where are the asymptotes? It's
Every pi over 4.
No.
Pi over half.
Yeah, pi over 2. Because that's where cosine goes to 0. So that's where it's going to have to go to infinity. And it looks sort of cubish. So what does inverse tangent look like?
From
Where are the asymptotes going to be now?
1 and 2.
Right? Doesn't an inverse function just flip this thing over? So this asymptote gets flipped there. This asymptote gets flipped there. The whole thing gets flipped.
Sure.
Yes, no, maybe so.
Yes.
And then it goes. That's awesome. So then limits to infinity are easy as hell on inverse tangents. Right? So the question is over something. N. So the limit as n goes to infinity, this is easy. This is not indeterminate. This is completely determinate. So on
Pi over 2 over infinity.
yeah. So this would go to 0 because it would be pi over 2 over n, and n's going to infinity, so the whole thing goes to 0. The top becomes finite, the bottom becomes infinite, totally determinate. Let that sink in. Yeah, I had some people, I think, I did grade a few things, and then I decided, why not? I'll leave them in my office. But I graded some people, and one person did try to take the derivative here, but L'Hopital's will not guarantee the right answer if you don't start with indeterminate form. All right, so then it's not L'Hopital's fault. All right. He's dead too, so it doesn't. As far as we know. Leave it open. Never know. All right. Anything else from homework? Okay, all right. So let's look back at this. I think I remember now that we did get through geometric. We did that last one, the 1 minus 3 halves plus 9 fourths. Because there the r was bigger than 1. So just to remind you guys, I mean, it's on here. But the beautiful thing about geometric series, and this is not true for most series. And in fact, I am going to try to transcribe. Euler did some work with series. I'm going to try to transcribe some of what he did, because to just take a general series and then actually try to figure out what it converges to is unbelievably difficult. Geometric series are easy because there's sort of a pattern to them that we can exploit, like we did last time, and figure out what the sum is going to have to be. But a general just series you just make up on the fly to actually figure out what it converges to, holy shit. It's not easy at all. It's totally possible. Totally possible. But remarkably difficult. So for example, you figured out what this converges to, but nobody in the history, in the world, at the moment, and throughout all history has ever figured out what the hell that converges to. And you're like, well, they're not really that different. Oh well. So we know what this converges to. Nobody has a freaking clue what that converges to.
Why?
What do you mean, why?
Because
We were surprised, actually. I'm sure they were surprised. They're like, holy shit, we figured that out. Whoa.
What is that?
See if I remember. I think it's pi squared over 6 or something remarkably, unbelievably unexpected. I think at some point they tell you in the book, but I can't remember. But I'm going to try to, I think that's the one I'm going to try to show you. I'm going to try to print it out. You're never going to have to do anything with it. If you don't even want to look at it, you really don't have to. It will make a little part of me die that you don't even want to look at it. But that's up to you if you want to have that happen. But at least just to look and see. And because there was a book I was reading that I kind of agree with. In art class, do you freak out when they show you a piece of art that somebody created? Do you? Do you go, ah! But if I show you a mathematical proof, I think your brain goes, I can't do that. Shit! But you don't think that to yourself. When I watch freaking, Curry doing his shit on the basketball court, I don't go, oh, I can never do that. No, I just go, wow, that's amazing. Holy shit. I can never do that. So I like the idea of presenting artwork, that the mathematicians have done, and just appreciate. Maybe you don't understand this. I don't understand how somebody did some things in this painting. What the hell kind of brushboard are they using? Holy shit! I don't know. I don't think about it really. I just go, wow, the end result's kind of nice. So I'm going to show that to you, just so you can, if some of you are very curious, you can try to follow it along. It's not impossible to follow. It's not impossible. It's actually not crazy hard, but it's not something somebody would automatically think of.
Wouldn't it be the smaller, the higher the power on the bottom, will be closer to 0?
Well, the higher the power on the bottom, the quicker it goes. You would expect the result to be smaller,
Yeah,
right?
small numbers.
So the sum of 1 over n cubed is probably small. It's got to be smaller than the sum of 1 over n squared. Does that make sense?
Yeah, but
Of course, because every term is going to be a little smaller than the other one, right?
yes.
It's not going to be 0 ever because it's finite. It's non-zero forever. But it's going to be smaller. All right. So I'll try to figure out how to give that to you in a nice format. If I give it to the original format, it's very hard to follow. Okay. Oh, so the last part of this, we've talked about this, and I know I made a big point of this. I can't make a big enough point of this. What can you tell me, if you know that this converges, what does that mean about this?
Goes to 0?
Good. So if this, then this. So if the limit of an is 0, what can you tell me about this sum?
Nothing. It might or might not convert.
Yeah, but the key thing, say again?
You can't. It might converge.
Yeah, you can't really say anything specific, but at least it has a chance.
It might or might not. Work more.
But too many people say, oh, this is true, therefore that converges. Next problem, oh, cool, it's the same thing. That was quick, that homework was easy. And then you die in the test. You guys with me? It's really hard, especially part of what we're going to learn today. It's a two-step process where the first step is so simple, and the other step is this. And then the result is it converges. So I almost don't blame you if you start to think, that means it converges. No, but it doesn't. It's a very specific type. It's called an alternating series test. And alternating series are the ones where it has -1 to the end. So if that's true, should it be easier or harder for it to converge, do you think? If every other thing is negative, it should be, what do you think?
Easier.
Easier, because it's subtracting from itself every other term, right? So it's like I'm growing, I'm shrinking, I'm growing, I'm shrinking, I'm growing. So it should be easier for it to converge. It should be easier to prove that it converges, right? Okay, all right. I like that. I'll take that as sure, man.
Yes, sir.
Yes, sir, is the other form of that. Okay. Blah, 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 blah. So what's the first thing you do then? Anytime I ask you, determine whether this series converges or not, the very first thing you check is what?
The limit.
The limit. Because if the limit is not 0, it diverges. That's the test for divergence. You do that first, because if the limit is not 0, you're like, oh, I'm done. It can't converge. There's no way it can converge. I'm done. I don't have to do anything else. If it is 0, oh shit, I got to do something else, right? Seem to be making a big deal out of this. Seems to be something that messes people up. Okay. Oh. So if there's no other questions, I'm just going to get right into 11.3. Yep, cool. We're ready for it. Here we go. I've already talked about 11.3, to be honest. To you guys, not just to somebody else. 11.3 is the idea of the interval test. And what this says is whatever the associated interval does, so does the series. So what I used this on before was, if we were looking at this guy, and I want to know what that thing does. Just remembering what this looks like, here's 1 over x. So that's the associated function, right? And if I look at it from 1 to infinity, so if I, how long is this? Oh, which way do I want to go with that? Yeah, I could do that. So this looks like Riemann sums, right? So think about this. If I calculate the integral from 1 to infinity for this function, and it diverges, what's true about the series? Is it bigger or smaller than the answer to the integral of the function? Every single one, are they over or under? So then the blocks, if I add up the blocks, it'll be bigger. So sure enough, we did this earlier. We did the interval 1 over x, 1 to infinity. We've done this before. We get ln of x. Ln, t is the infinity part. This diverges. Therefore, since this guy diverges, so must the series it came from. We'll let you digest that for a second. All right. So I want to pull some animations up. So you guys do the exact same thing. Why do you think I got to start at 2 there? It's nothing major, but why? What would happen if I try to start at 1?
0.
Yeah, ln of 1 is 0, so I just got to start at 2, just so I don't get infinite. Do the exact same thing on that. Try it. And let me pull this up here. Holy shit, where am I? Oh, there's. It's like, where'd my camera go? Oh, it's over. And Jeff, just go to Chrome, man. We're going to try Firefox. So what's happening there for that guy? How do you? So if you want to integrate this is a small point, but I am gonna do it enough. I might take some points off. I mean, what did I do there? Small point.
Change the ends.
Yeah, I got to change ends axis so I can actually integrate this thing. Right? It's got to be somehow connected. It can't just be dots hanging out, because in the area would be nothing. So I'm going to change it to a real variable. And then how do you integrate this? No. Yeah, u sub. Because there's a function in there whose derivative is in there. That means u sub will work. So you always want to rule out u sub, and I can't rule out u sub, so I use it. So u is ln x, du is
1 over x.
dx, so then you get integral 2 to, we'll do the t thingamajig. This will be 1 over u du. And that interval is ln. Good. So it'll be ln of u, which is ln of x, from 2 to t, letting t go to infinity. So I get ln of t minus ln of 2. Well, ln of 2 is just a number, who cares? But ln of t, as t goes to infinity, that goes to infinity unbelievably slowly. But that's all it takes. Divergent. So remember, if this would have been n squared, what do we know about that series? We've proven this one too.
P is greater than 1, therefore it's greater.
Yeah, so I haven't really put it in this form of a p series yet, but if the power is bigger than 1, this will converge. So if this was n squared, it would converge. You guys with me?
Yes.
All right, we've talked about that one before. So what's weird is ln of n goes to infinity so slowly, it almost is like multiplied by a constant in a way. Because if I multiply by if I make n's power go from 1 to 1.0000001, or one of our favorite things, 1 plus epsilon. Remember epsilon?
No.
That's too bad for you. Epsilon is greater than 0. Normally it's remarkably small is what we consider it to be. So if I had this, that would converge because the power is bigger than 1.
That's a p series, isn't it?
Yes, p series, good. I haven't really said that yet. We're about to prove it. So what I want you to do right now, is everybody with me on this? Do you guys do this all right? I mean, that wasn't horribly evil. It could have been much, much worse. You got to be careful about how you handle this infinite integral, right? But that definitely goes to infinity, so this is going to be divergent. Therefore, this series diverges. What the integral test requires, though, in order to use this test, I haven't even told you what the requirements are. There's 2 things. Maybe I should give this to you. Well, maybe I'll give this to you in a minute. F of x has to be decreasing and continuous. Those are the 2 things that have to be true in order to use the integral test. So for any of these kind of things, this is obviously, as n gets bigger, that's obviously getting smaller. It's an inverse relationship with n. So as n gets bigger, that's decreasing. And it's continuous. We know it's continuous on its domain. Any rational expression is continuous. All right, you guys okay? You guys are like, what is happening? All right.
Question.
Yeah.
For ln of t, is there any way to do you just have to know that it goes to infinity, basically?
Well, the thing is, ln of t goes to infinity because ln of infinity is so ln of something that's going to infinity will itself go to infinity.
Okay.
So if you had ln of ln of blah 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 of t, that would go to infinity unbelievably slowly. Right? Like, it's been about 18 billion years. Where are you? I'm at 2. Oh shit! All right. But you give it an infinite amount of time, it's going to make it to infinity. Yeah.
In order to do the integral test, should we decrease in n continuous
Yes.
or
No, and. Yeah. Cool. So let me see what you guys can do with this. Let me finally close the door and get this official. Figure out what must be true about this using the integral test in order for this to converge.
P is greater than 1.
I love that somebody just gives up on that. Should have said, that's it for me, man. I'm out. It's not a quiz. It's not even homework. I never have to look at the work it's going to do. Try to use the integral test on this. maybe start by making sure this is true. What has to be true about P in order for that to be true? What's 1 over square root of n? Is that decreasing? Of course
No.
it is. So I appreciate the no, but no, it's not right. As n gets bigger, square root of n is getting
Bigger.
Bigger.
square root of 4 is bigger than square root of 1. Right? Come on, guys. Come on, guys. Come on. Don't anticipate what you think I want you to say. Think about the problem at the moment. As n gets bigger, square root of n is getting bigger, right? Because it looks like that. So 1 over square root of n is getting smaller. So the power here, though, is 1/2.
It has to be larger than 0.
Yes. The minute the power on n is 0, what is that really?
Constant.
That's 1. Is that decreasing?
Don't know.
No. So these requirements, even to start the integral test, tells me that P's got to be greater than 0. Now, assuming P is greater than 0, apply the integral test. Do it. Do it. I know it's not a number. I don't care. You can integrate that.
Okay.
Alright. Here we go. So now I know if P is greater than 0. Yeah, might as well bring this in there. The limit as t goes to infinity, integral 1 to t, 1 over x to the p. What is that integral?
Ln of x to the p over px
Alright.
minus.
So assuming P is not 1, for example, because that brings in the ln. We've already proven that that doesn't converge, right?
X to the p plus 1.
Yeah, this is a power rule. The only power that would bring an ln into play is the first power, and we already know that that diverges, right?
So it's x to the p plus 1 times 1 over p plus 1. P plus 1.
And that'll be from
0.
1 to t.
That'd be negative. Wouldn't there be a negative in there somewhere? This is in the denominator.
Oh, yeah. That's right. This is x to the negative p. So it'll be x to the negative p
Plus 1.
plus 1 here. Thank you.
I mean, it doesn't matter if p is positive or negative. It doesn't matter if p is positive or negative. Anyways, you're adding 1. Because if it's...
Oh, no. It doesn't matter what p is, but whatever p is, this expression is x to the negative p. But remember, we also went into this assuming that p is positive. It's got to be, or else the requirements aren't even met. Right, cool. So then this will be limit as t goes to infinity of x to the negative t plus 1 over the negative t plus 1 minus, if I plug a
X,
I'm being real here. Jeez. This will be like a t in for x, negative t and negative p plus 1, that was really freaky. Minus, like a 1 in for x. And of course, that'll just be 1 over that. Yes, sir.
I don't get why it's not ln.
The only power on x that will bring an ln into play is the first power. And I'm just going to throw that one out because we already investigated that. We know that that diverges. And I'm trying to find out what does p have to be to converge. Does that make sense? So if I had the, if I had the integral of 1 over x to the 0.9, this is so desperately not the natural log of x to the 0.9. That's complete bullshit. I really want you to realize that's so wrong. And this is where we just extend this to be anything down here goes into an ln. That can't be right. If I check this will be 1 over this times the derivative of this. And the derivative of this is 0.9x to the negative 0.1. It's not going to be this. Maybe? Yes. Okay, so we already know that diverges, so we'll throw that case out. So there's not going to be any ln. It's going to be the power rule that we apply. Cool. In order for this thing, so this is finite. Who cares about that? In order for this to not go to infinity, since t is going to infinity, this has to end up going down. This has to end up being to a negative power. Which means this power has got to be less than 0. Right? The negative p plus 1, I really want this understood. If t is going to infinity, if this power is positive, this whole thing is going to go to infinity. It's going to diverge. So the only way for this to converge is if this power is negative. Because that'll bring that down. That's over infinity. It's going to go to 0 then, right? You got to bring this bad boy down so that it doesn't go to infinity. It actually goes to 0. So negative p plus 1 has got to be negative. And when you solve for p, it's p greater than 1. So as long as the power on the end, if you're looking at the series, is bigger than 1, the series itself will converge, and that's just called the p-series. That is its own little test you can apply now. So if I ask you, from this day forward, unless the problem specifically states, prove it or something, if I say, does this converge?
Yes.
Yes.
Yes, it does. What's it converge to?
Who knows?
Nobody in the universe that we know of can tell you.
In the universe?
That we know of. Do you know somebody else in the universe? If you do, call them up. Speak in their language.
You never know.
If it's, I don't know what it's going to be. And then they can tell you. Right? If you translate it for us. But yeah, at least we know this converges. So for a while, our immediate future is going to be, does it converge or does it diverge? And if you want to know what it converges to, too damn bad. I mean, it's just what we have to accept for a little while. I'm going to show you, like I said, what it takes to show that's what exactly some of these things converge to. And some of them, like maybe that one, it's impossible. Not just hard. They're not sure about that guy. But it's impossible to figure out what it converges to. I mean, you can estimate it. You can get the decimal approximation, but and you can kind of estimate what that's going to be, but there's just no way to prove, to show by hand what it converges to.
What happens in a calculator that you plug that in and you say evaluate? We'll just say error or...
Oh, if you did what now?
If you plug it in a calculator to solve it, or Wolfram Alpha.
Oh, yeah, they would say, what the hell? It's sort of like if you plug in the first several prime numbers and then ask it to continue the sequence or give it... It can't, because that's, of course, what every mathematician in the world in their free time tries to figure out, including me, is there a pattern to the prime numbers? We know a lot of shit about prime numbers. We just don't know how to predict what the next one's going to be. You guys know that? There are actually computer programs that in your downtime, instead of a screensaver showing up, there'll be a little crunching thing that'll crunch to see if the next number up is the next prime. It'll determine if it's prime or not. So it's these distributed computing things. Have you ever heard of those? Mm-hmm. There's actually one that tests protein folding to see if it can find a cure for cancer. So you can download that. And when your screensaver would come on, it actually uses your computer's power to analyze protein folds and see if it'll find a cure for cancer. Or there's one for SETI. Search for Extraterrestrial Intelligence. They send you all this frequency data they got, and your computer crunches it, and it sends back its information just to see if it can determine if there's any signals that look like they're extraterrestrial in origin. You guys look up distributed. I think it should be distributed computing on Google. They're free because they want to use. If they can just use everybody's computer, it's like they got the biggest supercomputer ever. And it's just dedicated to finding this, So the cure for cancer sounds worthwhile. Instead of little toasters flying on your screen, or that's old school. But you could actually have like this cool protein folding thing happening on there, or Fourier series transforms on signals to see if they came from aliens. It's really nice. Or the Mersenne or the Prime project to see the next prime number.
Is it like mining for bitcoins or something like that?
Mining for bitcoins. No.
You kind of rent your computer and it's just running.
Oh, I see. Yeah, so it's a general idea of letting somebody else use your computer's computing power. Yeah. But it's not quite the same theme. I like that though. Okay. Alright, so that was a lot of crap to go through, and I know a lot of you guys who are not terribly interested in that, but this is really powerful now. So if I ask you, let me see if you guys can handle this.
Divergence.
Now, the only reason you should be upset is if you have trouble with fractions. And if you have trouble with fractions, you have trouble with your placement. You understand what I'm saying here? I mean, what do you do to this? I don't understand why you guys, not you guys, but people in 280 should not have any trouble simplifying this expression.
Brings up the
How do you rewrite end of the 15/7? Oh, I just
15/7.
When I look at that, that's what it says. So I couldn't even stop myself because that's just what the damn thing says. That is n to the 15/7. And then what do?
Subtract it.
Subtract. What's 3 minus 15/7?
N to the 6,
Little less
7.
than 1.
Yeah, so it'll be 1 over n to the 6/7. So that is divergent. Cool. If you just put it in the right form, you can tell what's going to happen. So now that we know things in this form, we can determine what they're going to do. A big chunk of some of the homework is going to be put the damn thing in that form. And then you can see what it's going to do, right? All right, so P-series, very powerful, but they don't often exactly work with what you're doing, but some of them are going to be just like this. All right, so now we got that under our belt, P-series. Cool. Well, let me go ahead and give you this handout. I keep thinking I should, so I'm just going to. This is crazy full of information, so just try to look it over. And I wanted to show you an animation, but it won't let me. It's on Wolfram, it won't let me install the freaking player. So that's really, really stupid. Oh well. Have to figure that out. So what we've already done is at the very. Oh. No, the quiz is only going to be on 11.1, 11.2. Sequences and series. We're just 11.1, 11.2. Thursday. All right, don't forget. Yeah, so we won't have any 11.3 stuff on it because we're just now getting into it. Yeah, because it hooks under there, so eventually it's just kind of stressed out. All right. So we've already talked about the top, the interval test. The remainder estimate is kind of nifty, and they talk about that. This is still section 11.3. Let's see where they have the remainder. Here we go. So, if you have one that converges, like 1 over n squared converges, because p is greater than 1. And if you go from, let's just start at some n. So this would be n plus 1, n plus 2, and so forth. So this converges, therefore the series below converges, right? And I'm going to come back to this point, because somebody, I don't know if anybody out there is like, well, when do you pick when it goes over and under? It's going to make more sense when we talk about the direct comparison test. We have a little flexibility there. So stay with me. So this integral from n to infinity, well, let's say f of x, where f of x is related to a n. This is replacing n with x, like we've been doing. Is that cool? Okay. To estimate the error in this, it's going to be, if I go from, let's see, n plus 1 to infinity. And again, this is on, these pictures are on page 718 if you want some that are nicer. And I go over this time. So the error is actually going to be somewhere in between going from n to infinity and going from n plus 1 to infinity. So that's a little bit under, that's a little bit over. So you can see why, actually I've got these backwards now. The remainder, the error in this thing is going to be in between those two intervals. Yeah, and of course, what I'm alluding out here is, if I use the first n terms, so this Rn is the remainder of what happened. So I've got some S, which remember from last time is the actual sum of the whole series. So if I go out only Sn, so if I only go out 4 or 5 or 6 steps, then that means I haven't gotten all the way to S yet, because S I got to go to infinity for that. If I subtract those, that's what Rn is. So if I use just the first n, that'll be Sn, to figure out what the sum is, then Rn is going to be how much I'm off by from the real sum. So I can't figure out exactly what it is because I can't use integrals to even figure out exactly what the sum is. I can only use integrals to see if it looks like it's going to converge or diverge. Cool so far? Sort of. All right. So if I use the first n terms to figure out what an estimate is for S, then for example, from n up, that interval is going to be higher than this, the remainder. The remainder would be these boxes here. So this integral from n up would be larger than that, so that's why it's up here. It's bigger than the remainder. So remember, the little boxes are the actual sequence terms, right? The little box dudes are the little sequence terms. Remember we talked about these are all one big, and they go up as far as the first, the second, and third sequence term. You guys remember that? We talked about this before. So it depends on you remembering that fact. So don't, when we first talked about integrals, using integrals to estimate from 1 to infinity, I wanted to point out that, like if this is 1 over n, or 1 over x, I guess, is the associated real function, then this would be 1 here, right? So this would be 1. That would be the first term in that sucker. And then this would be 1/2 here, right? You with me? So then the area of this box is the first sequence element. The area of the next box is the second sequence element. So the box areas are the sequence elements. When you integrate, you're kind of approximating what the addition of those boxes would be. And that felt like the connection between Riemann sums and integrals themselves from before. We just don't take the step of letting the boxes get crazy small. We don't want to. We want the areas to represent the actual sequence elements. So if I use, so see how this starts at n. So if I use this little piece to estimate what the sum is to get Sn, then from n up, the integral, and of course I just, as I did it, I realized I'm erasing the damn thing. This is this integral of this function, and that's bigger than the area of the leftover boxes, right? That's the area of the leftover boxes. So that is bigger than what the remainder would be. And this, of course, if I go to n plus 1, these boxes are, the integral is smaller than the sum of those boxes. So the actual remainder, the actual amount that I'm off by, is somewhere in between those. So I can actually calculate bounds for how far I'm off by. Oh shit. All right. Yes, sir.
Well, are you going to do an example with this?
Sure.
Because when you, I don't know, when you put like n plus 1 and n, it kind of just like hard to visualize for me.
So there's the one here. I want to sum. All right. So if I only want to go up to the fourth sequence element. So you guys help me out real quick. It should be very quick. Can you go ahead and just do that sum in your calculator? I mean, it's going to be from 1 to 4, so it'll be 1 over e squared plus 1 over e, and now n is 2 to the fourth.
Here, you said?
No, just figure out what that sum is. That's all. I don't hear any dissension.
Sorry,
in the
point
ranks.
1, not 1 point.
Oh, point 1? That makes more sense, because 1 over e squares are already just 0.1, and then it gets really crazy small. All right, how's that so far? That's pretty simple. That's just the first 4 elements, add them up. That's all it was. Now, before we do this here, what kind of series is this?
P series.
So this is S4. It's not a P series. Why is it not a P series?
Because it's a logarithm.
Is it n to a power?
It's exponential.
Oh,
No, it's exponential. So it's not related to the P series. So it's got to look like n to a power, not a number to an n power. That's an exponential function, right? So be careful. Just like when you integrate, you got to know what form it is before you can figure out what to do with it. Now, what kind of series is this?
Geometric.
Geometric. What would R be?
1 to E squared.
Yeah, what do I keep multiplying by from here to there to there?
1 over E.
1 over E squared. Is that, you guys see that? I just keep multiplying by 1 over E squared to get to the next term. And of course, if I take an n power out, I see 1 over E squared to the nth power. Like that. Is that less than 1? Is R less than 1? 1 over E squared, is that less than 1?
Yes.
Desperately so. So will this converge or not? Yes, because R has to be less than 1 in the absolute value, of course. But R is 1 over E squared, which is less than 1. It'll converge. Sweet. And I exactly know I know exactly what it's going to converge to. What's the little formula for geometric sum? Don't worry, we're eventually going to get here.
R minus 1 minus R.
So what's the first sequence element?
1 over E squared.
And R was,
1 over E squared.
so if I multiply by E squared, I get 1 over E squared minus 1. Somebody help me out there. Is that, you guys see that? This is not amazing math. This is just workman's math, right? Just blue collar math. Ah. So what's 1 over E squared minus 1? What is that? Somebody help me out. 0.12 something. I don't know. I can't. Yeah, it's 0.1.
0.156.
Okay.
5.
Blah, blah,
I could some others.
All right. So how far off were we? Only going out 4 elements. How far off were we? Well, go out a few more steps there. 1565.
176.
All right, and this was 15647, and who cares? That's plenty. But we got really damn close. It's like 0.00004, almost 5 off, right? So the error here is about 0.00005, roughly. The error, the R4. Let's see. So only using the first 4 elements. Since 1 over E squared, that kind of thing is going to get small real fast. I didn't need a lot of sequence elements to get to its sum really close to it. You with me? The slower this guy goes to 0, the further out I've got to go to estimate where it's going. Think about that. That only makes sense. Okay, so now let's see what this guy says theoretically about this. And I want you to understand, we can't always do this. Is geometric. Boogie woogie. So I knew the form of the actual sum going to infinity. Just some random series, I'm not going to have a freaking clue. So I'm going to have to use this to estimate the number that we actually know is real. So let's see if that falls in between these two like it's supposed to. So what's the interval? Now what's n plus 1 going to be? What's n?
1.
No. And this is where it's a little bit, the book does this is why I did this too, but they use n even though n is used here as a variable. N is going to be the total of it's going to be 4. Right? They should have used k like our cave dude. Is where we stop.
I see.
You understand? They used n double duty here, but n in the remainder theorem is going to be how far out you went. So we went to 4. So the integral, this interval is going to go from 5 to infinity, and I'm going to put that as the real value function. That's less than or equal to Rn, which is less than or equal to integral from 4 to infinity. And just to get to the chase, cut to the chase.
Is that a bite?
Where am I looking? Here?
Yeah.
Yes, totally. I was actually proud of that 5 at first, but maybe not. Maybe I shouldn't have been. Shit. People at home are like, you can hear what's going on. Integral of this is just e to the negative 2x, right? So what's the integral going to be?
E to the negative 2x over negative 2.
All right, good. All right. And that's from 5. Let's throw a t in there just to be all official. All right, and that's going to be less than equal to Rn, which is less than equal to the limit. And the nice thing is we've already done the integral. This is negative e to the negative 2x. Oh, not negative, but it's up there, Jeff. Yes, it is up there, Jeff. Stop talking to yourself, Jeff. All right. And this is from 4 to infinity, 4 to freaking t. So desperately, even if you didn't quite understand the little details, the integral approximates the sum of the series, because integrals came from summing up a series. So the integral starting at 5 and the integral starting at 4 bound the actual error for that going out only that far in your series. Because they go, well, the rest of it should be approximated by either this integral or that integral. So the rest of it's going to be approximated, is going to be somewhere between those two, how far off you are. So let's see what we get here. We get something now. When t goes to infinity, e to the negative infinity basically is going to go to, you can do it, that would flip down. It's going to go to 0. Good. So then I plug a 5 in, so it's minus negative, so it's e to the negative 10 over 2. Is that cool, plugging a 5 in?
Yes.
Is less than equal to Rn, I keep saying n, but it's 4, we know. Is less than equal to, same thing over there, except with the 4 going in. So somebody help me out. What is e to the negative 10 divided by 2?
Should you have negatives in front of that?
No, because that went in first, and then it's minus and negative for the second limit, right? Otherwise, that'd be really weird. You went past being close. You're so accurate. You're like negatively accurate. So, holy shit! You're more right than you could possibly be.
0.50 to 2699.
So 1, 2, 3, 4, 5, and then 2, 6, blah blah blah.
226.
Sure. And then what about this guy?
Negative 8. 4 zeros and then 167.
And then we were actually off by 4 zeros and a 5. Well, shit. I was hoping this would come out nice. You sure about that?
Well, the first term that I gave you, the 15647, I rounded to 7, so that's actually a 6.
Well, that's all right. But what 1, 5, 6?
The Rn
No,
is
no.
wrong.
Oh, this is 7.
No, up top. That's
This guy.
Yeah, the 7 is a 6.
Oh, well then, let's see. All right, that 7 is a 6.
And then there's some
Okay.
other number.
Anyway, all right. Shit. But these will be the boundaries, upper and lower boundaries for how far off you actually are. Which one do you think we're most always concerned about? Do we want to know what our error can be, the smallest our error can be, or do we want to know the biggest our error can be? So very often we just calculate this one. I know I'm wrong, so don't tell me it's at least you're off by at least. No, I don't care. I want to know how much I'm off at most by, right? So very often we just do this top one. This would just verify that I'm wrong. Okay, I know that. Normally I just want to know how off could I possibly be? How bad could it possibly be? Does that make sense by itself there? Yes?
What's the answer supposed to look like at the end of all of that?
What should have happened, and I wasn't careful enough asking you for these values, is that should end up in between these two. Because this is supposed to bound the error. So the error we actually get should fit in between these two integral values, because those are supposed to be the max and the min error. So the actual error has to be somewhere in the middle. All right, let's go past that. Let's get to something a little less weird. When do you? Please understand the remainder theorem, the little p-series proof. Those are all extra stuff. The integral test itself is stupid simple. Whatever the associated integral does, as long as your function meets the requirements, your series will also do. Unbelievably simple. But can we integrate every function there is?
No.
Hell no. So we can't just rely on the interval test alone. You with me? The interval test, I can't just take what it says. I need something to help me when I got intervals I can't do. Okay. Also, before I get too far away from it. Oh no, that's cool. All right, didn't do that. Good. So the next thing here is the direct comparison test.
This
You guys
is going
mind?
under 11.3.
Let me remember. No, 11.3 is just interval test.
It's on.
11.4 is comparison test. And to be honest, I forgot the very last thing here is in 11.5, the alternating series test. Now, and this kind of relates back to parts of the interval test. But I think I've said this before. Let's see how do I approach this? If I know that this, let's say that this is the function related to sum of A. Let me see if you guys are cool with that quick way. That's a quick way to say sum n equals 1 to infinity of A sub n. That's just, this is the function related to this series. And I know that this converges. And I have this other series, like that. And that's related to sum of B. What do you think has got to be true about the series made up of B? What's got to be true about this? Why must it converge?
Squeeze.
It's not really squeeze. It's actually better than squeeze. It's just the ceiling. Yeah, this is this guy's ceiling. In order for this to diverge, he actually has to somehow get above. So what I'm implying here is that the elements from A are always bigger than, or at least as big, as the elements from B. And to be honest, it only has to happen after some point. Well, shit, let me not do that. That goes a little crazy. Keep it like this. Shoot. So here at 1, they are there. And so that might be over it for a little while, but who cares about what they do in the first finite number of terms? I can just kind of cut those off and say, okay, that's 7, who cares? The rest of the way, if this guy converges, this guy must also converge. So if you're reading that little handout I gave you, this is so nice if you let it be, yeah.
Is this always the case? Is there no function that towards the end it starts to diverge?
No. I want you to understand. This is always true. Given that this is always true, then if A converges, B must also converge. Because if a bigger series converges, a smaller one must also converge. There's no way it could go to infinity. I know I got less stuff, but I'm richer than you. No. It's no good, right? You guys kind of with me?
I mean, you can prove that with P series, right?
Well, no, this works for any series. Well, you could use P series. You could use this for P series, of course.
To prove it.
To use the direct comparison test, I have to know something about. I have to know whether this converges or diverges. I have to go in knowing that, so I could use a P series to compare something else to.
Right.
So, and of course, this works the other way around. If I had a function that I know diverges, and I have some other function that's always at least as big, let me put it up here. Wow. So if this diverges, what must be true about sum of B? It's got to also diverge, right? And that's the idea of a floor. So if the floor goes to infinity, what can I do standing on the floor? I'm going to go to infinity. I don't have much of a choice, right? I don't have any tools to break through the floor. Shit. Right? I'm always above the floor. If there's a ceiling that converges, there's no way in hell I can diverge. I keep bouncing off the ceiling. And it just pushes me down to converge. How we go so far? All right, now, of course, that's the theory, and you're all like, okay, that seems nice, but what the hell does it look like in practice?
Are the letters for the first part of this swap, because says it B of n converges to A of n converges? Did you write
No. So the first part of this is like, this first part is kind of my attempt to just very quickly summarize what the boxes below say. So the little, suppose that sum of AN and sum of BN are given. They're positive terms. And we got 0 less than equal AN less than equal BN. So BN is bigger than AN. Which one of these could be the ceiling? B could be a ceiling for A, right? Because B is bigger than A. And which one could be the floor? A could be the floor for B. So when do I want to find a floor? When do I want to find a smaller function? When I think this function I'm given diverges. I want to find a smaller function that diverges that will prove. If I think my function converges, I want to find a bigger function that's easier to show converges, because then that'll prove my function converges. And I try to make a point about, when you want to find which. So if I suspect AN converges, I'll try to find. So up here I write very quickly that if this is true, if BN converges, and it's always bigger than AN must also converge. I'm not going to rewrite what I've got up here on this handout, but that's the idea. Right? If the bigger dude converges, the smaller dude must also converge. There's no question. Okay. Yes, sir.
So it must be the case for the second graph that A is less than B.
Yeah, I'm sorry. So up here I was just using like two different. I think that might have been your question. I don't know.
Yeah, it was because the top one you're saying A is the ceiling, but in that you're saying B is the ceiling. That's why I was
Just because of the way this is written.
Yeah.
So over there I had A greater than B just
Right.
because of the way I wrote it, and this one A is less than B. Yeah. But you just always have to be able to find a floor and a ceiling. It doesn't matter who you call A, who you call B. So let's see how this thing works with a real example. And this is what I was warning you guys about before with the inequalities and getting used how to work with inequalities. So for example, and if you let it be, these are actually not that horrible. What's your gut tell you about this? I mean, what fundamentally, and this is kind of like going to your point earlier, what is this trying to be?
P-series.
Yeah, you guys see that? This is like if that wasn't there, this would be a P-series. Would it be convergent or divergent? So we suspect, you got to go into this with a suspicion. Do you suspect it converges or diverges? If you have no idea, you can't do shit. You got to have an idea. Because the minute I have an idea, I suspect it converges, that means do I want to find a floor that'll push me or a ceiling that'll contain me? I want to find a ceiling. I want to find a larger function that's easier to determine if it converges or diverges. I have no theories about n to the p plus rad n. There's nothing about that. So I need to kind of relate this to some other function that's easier to state directly whether it converges or diverges. So this one's kind of easy. If you let it now. So here's my, whatever you want to call it, bn, an, I really don't care. I know I want to find a bigger function. So which direction do I want the inequality here to go? Yeah, at least at least as big as this. I want something bigger or equal to this. Now, yeah, here's what's really nice. Here's what you got to realize. Since this is plus rad n, if I took that away, is the result bigger than this? And when I divide by less, my result gets bigger. Okay, that's the fundamental idea that you have to know and just be able to just go with. If you have trouble with that idea, this is going to be really, really hard. But if I'm dividing by less, then this inequality is true. This is what I was saying when we're doing math induction. We're going to get to a point where you have to be really comfortable with the inequality. Why was I allowed to get rid of this rad n? Because I got a lot of flexibility with this inequality. Now, if you go too far, that's true too, but what the hell does this do?
Diverge.
Yeah, this diverges. But I wanted to find a ceiling that converges. Shit, so I went too far. So it's not, sometimes it's not that difficult because it's just screaming at you what the hell it wants to be, so you just kind of like help it in that direction. So I found a larger function. What does this do? Convergent. Be very specific. Convergent what? P series.
Oh.
P equals 3 greater than 1. You understand what I'm saying there? Don't just say convergence. You better tell me why, right? It's not good enough to say because you got a 50-50 shot. I want you to be better than that. I want you to get it right for the right reason. Convergent P series, P is 3 greater than 1. Therefore, what?
1 over n cubed.
Therefore, this thing
Converges also. By P series.
converges by
By direct comparison.
direct comparison test, DCT. Oh my God! Don't even try to say that's a lot of writing. Trust me, it is
What
not.
do you mean that?
What's up? You okay? I don't believe you, but you said yes. I'm going to keep going. It's up to you. What's up? Yeah.
Why did you choose P equals 3 greater than 1? That's what
I didn't choose it. What is P?
3.
I didn't choose it. It's 3.
Why greater than 1? I mean,
What's the P series test? What has to be true for this function, for this series to converge? What's got to be true about P?
That'd be greater than
Good. So
1.
that is now part of your toolkit. That's now something you know. You can pull it out whenever the hell you need to. Don't go anywhere. I mean, I say something like that. I wait to see who's got their minds in certain places. All right. All right. So this now I know. So if P is greater than 1, I know I've got a convergent series. I needed a convergent series to compare this to a bigger convergent series to show that this guy converges. And why do I know this guy converges? Because this would make it converge. This is making it converge even better, if you really think about it. It's making this get big faster, so the whole thing is getting small faster, right? So of course it makes sense it's going to converge. Good. All right. See? Don't give up. I hate that shit.
No, I understood the
All right, good.
concept. I just forgot about the.
All right. Good. I just hate it when you were like, no, don't worry about it. Shit, just ask. Yeah.
So if it's divergent,
I love it. So I'm kind of forgetting. It's sort of like I always forget to see if there's a GCF when I first teach factoring, because I know there isn't. But yeah, I should always be making sure, is this limit 0? If it's not 0, I don't have to do shit. But of course, this limit would be 0. It's kind of obvious. I wouldn't even do the test. I'm like, oh, it's 0 for sure. I'm just going to get into it. You with me? But yeah, in general, if it's something else a little more complicated, I'm going to take a second and look at the limit. Because that limit might even help me later if it's not 0, or if it is 0, it might help me figure something out later. Okay. So what about, let's see. Before I forget real quick, we did number 3 up on the board, and one reason I wanted to do it before I gave you this is I made the n 1, right? Number 3 on the first page on the interval test. N was supposed to be 2. So you just want to make that a 2 for yourself, so later you don't freak out. It's my bad. Yeah.
So, he asked if it's divergent, you don't have to write anything afterwards? Or do we have to say, like, oh, it's divergent because the limit's not?
Divergent by divergent.
Oh yeah. So yeah.
Like, do we have to prove
Just
why
show me
it's
the limit's not 0 and say therefore divergent.
Alright.
That's fine. You can say by the test for divergence, but if the limit's, it's more of a theorem. If the limit's not 0, it doesn't have a chance.
Right.
And then we give it the name, the divergence, the test for divergence.
it's divergent because
What about number 2? It's on the back page here.
1 over n 4/3.
Wait, whoa, back page.
All right. Say again. I know what you said. All right. Yeah, so a good check. First, it does go to 0, which that doesn't mean you're done. It means you're not done. All right. It's only if it doesn't equal 0, then you're done.
Divergence.
The thing that people try to do with this that's not good is you can't just throw these off. You can't. That's not mathematically correct. But if we feel, what's our suspicion? We suspect this does what?
Divergence.
Why do you suspect it diverges?
Because the degrees are...
Because that, just kind of do it hand waving, it looks like it should be related to 1 over n, and that diverges. I like it. So I've got to step through this to be correct. If I think it diverges, do I want to find a floor or ceiling? A floor to push me to infinity, right? So I want to start with this guy and create something that is
Greater than, or less than, sorry.
smaller, right? So which one of these can I just take away if this is true? I want to make something smaller.
1 over n.
That's way too big of a step.
Plus 1. Just take away the 2.
No.
Take away the
If
one.
I take away the 2, I'm making the bottom smaller, which makes the whole thing bigger. If I take away the 1, I'm making the top smaller, which makes the whole thing smaller. Right? That's why I wanted to show you this problem. There's 2 things. Which one of these can you legally take away and the inequality stays facing the same direction? The skill of being able to play with these inequalities is important in several areas of mathematics. So it's not just this little thing you never have to worry about again. That's why I spend some time on this. So I can totally take the 1 away. Now here's the thing. The minute I show you this, I'll see if you guys really understand it. I can't just take the damn 2 away. Shit. So what I do is something so alien to us, but again, I have a lot of flexibility with this inequality. If I can't take something away, I make it like terms with the other dude. What do I mean? If I make the bottom bigger, or at least as big, because n starts at 1, right? So the minute n is 2, 3, this bottom is way bigger than this bottom. Are you with me? So that's what I mean. You can either legally take the damn thing away, or if you can't take it away, you can legally make it like terms. It's kind of nice.
Can you lower the power of the end of the degree?
Because then you've changed the p-series that you're going to. I really don't want to screw with these powers at all, because if I make that n squared or something, then it's going to end up at 1 over n squared, which converges, but I'm supposed to find a dude that diverges. Shit. Good question, though, but you got to be careful. You never want to end up in a place that doesn't do what it's supposed to do from the beginning. That might either say you were wrong with your suspicion, or you did weird shit there that you really shouldn't have done, like changing the powers. I almost never want to do that.
Okay.
See how I covered my ass there? But almost I can't imagine a situation right now. But
That makes sense.
I like it. It's my favorite phrase. So then, what's this equal? It's not inequality at the moment, because this equals, well, how do I simplify this?
n cubed
N over
over
3
3n.
Which equals?
1 over 3n.
Sweet. So that is bigger than that. This, what does that series do?
Divergence.
Divergence.
Good, because who cares about the 3? Just like any constants, we don't give a shit. 1/3 of infinity is still infinity. Infinity just got a glass. That's cute. So that diverges. You could say P series, P equal to 1. That's an equal to sign. Therefore, sum n cubed plus 1 over n4 plus 2 diverges by direct comparison. Because what's going to happen is we're going to learn more and more tests to use in different situations. You have to be very specific about the test you're actually using at the moment. To help me grade and to help you keep yourself focused on what the hell you're doing. Yes, sir.
Isn't that a... Oh, wait, no. Answer my own question.
I love that. That makes my job so much easier. All right. So, direct comparison is important, and I'm about to show you something that is related to direct comparison, but is often easier. But sometimes it's inconclusive, and then you got to go back and do direct comparison anyway.
Limit comparison.
Yeah, it's called limit comparison. So, I can't remember if they did. Yeah, they sort of did a proof in here, but the proof is kind of funny to me. If the limit as n goes infinity, an over bn, is that the way it goes? Equals L exists, and L is between 0. And this is a weird thing. What this, normally you would never see me write this, but this means it could get as large as you want it to, it just can't be infinite. If it's 0 or if it's infinity, this test is inconclusive. Go try another test. And that happens decently often, actually. So it's an easier test to use, which very often means it only works in certain situations. It's kind of the trade-off. So here's what's really beautiful about this. It can totally just clean house on these kind of problems. And why does this kind of make sense? The whole idea of comparison tests are all about how quickly or slowly things go to 0. The elements go to 0. And in fact, that's the whole idea of a series converging, is if the elements get out of their own way fast enough, if the rate at which they're going to 0 is quick enough, then the whole series is going to converge to something. You with me? That's why 1 over n does not converge, because it doesn't go to 0 fast enough, the elements. But 1 over n squared goes to 0 a little bit faster, it actually ends up converging. 1 over n cubed is even faster, and that's why p greater than 1 even makes more sense, because it increases the rate at which it's decreasing. I like that. That's awesome. Increases how quickly it's decreasing. So this kind of feels like comparing degrees of polynomials as a shortcut to figuring out horizontal asymptotes or what the limit's going to be. Right? If the degree is the same, if I got that, then the horizontal asymptote will be 3. The limit is 3. You kind of with me? Because both of these have about the same rate of movement. So they're going to agree at some number in between 0 and infinity. So that's kind of like why this makes sense. There's a very short proof, if you want to look at it in between, underneath on page 724, underneath the little box about limit comparison. But personally to me, it's really not that crazy of an idea. If we try it on this guy here, here's the beauty of this. If I look at this, the first step I used on this is really the first step I used to figure out what my comparison series is going to be. So what is this trying to be? What series is this trying to be? What's it trying to be? Be very specific. 1 over n. So if this is an, let bn be 1 over n. So if I think this diverges, I want my comparison series to also diverge, but in order for this to work, it's got to be something related to this. You can't just pick anything that diverges here and have the ratio tell you shit. You want this to actually be related to what this is trying to be. And you'll see why here in a second. If you make this ratio now, what happens? Put an on top and bn on the bottom. Is that cool? Here's the given an, and again, I don't care who you call A, who you call B. This is the series I came up with to compare to this. And why did I come up with that? Because that's what this is trying to be. What does that end up doing?
n4 plus n.
Yes, it ends up filling this guy in. Do you see that? So this would become times n. So this is the limit as n goes to infinity of n to the 4th plus n. I'm going to let you absorb that. You can see that. Because, of course, division by 1 over n is multiplication by n to the 4th plus n. And that limit's easy. That limit is maybe not so easy. 1, because these are same degree. So if the limit exists and it's between 0 and infinity, an and bn do the same thing, basically. I've got all the technical wording in there on the handout, but they do the same thing. So what does bn do? Converge or diverge. And our answer came out between 0 and infinity, so our original series also diverges. Yes, sir?
Why is BN 1 over n exactly? It's just because it's a bigger factor value.
2 reasons. I think this diverges, so my comparison must also be something that diverges. But I need this to be related to what this wants to be. If I strip away all the crap, it wants to be 1 over n, right? That's what we try to get the end result over there to be. We had an extra 3 in there we didn't care about. But doesn't this want to be 1 over n? When n gets really big, 1 and 2 don't mean shit. So that would be 1 over n, right? Good. So that's what it wants to be. So that's what I'll let bn be.
Please don't think I'm crazy, but you have like n to the third over n to the fifth, it would be 1 over n squared.
Of course, yeah, of course. Why would that? You're insane.
I wasn't
Wow.
sure.
Nothing I could do for you. But yeah, no, it's that simple. It's if I eliminate all the lowest degrees, I see what it reduces to. That would be my. If it's this kind of sequence, of course.
I wasn't sure about the thing though.
This limit comparison test works on all kinds of sequences and series. It doesn't have to be ratios of polynomials, right? So I have like a geometric series down there. I like this one. This is a good example of. So this is number 3. What's your gut tell you about what that does? Does it converge or diverge? Yeah, good. Right, because it's actually got more than what it needs to converge, right? Here's the trick, though. There's a bit of a trick to this type of thing. What would you pick Bn to be? So this is my An. I think it converges. My Bn has to be related to this. Why is this one difficult to do? Because it's kind of like a... True, but it would be easy if it was that. I wouldn't have to do any direct comparison. That's a direct geometric. But that's not a direct geometric. It's some kind of mixture, right? Hybrid geometric monster thing, right? So I want my Bn to be a related geometric that doesn't have the mixture thing going on the bottom. So what do you think Bn should be?
1 over 3.
So it could be 1 over 3 to the n? Or it could be 1 over 2 to the n, right? We just don't know. Which one do you think I should use?
Yeah.
Let's try it. Go ahead, try it. Do the limit. Set up the ratio.
So are we, with the limit comparison, we're not necessarily trying to create a floor or a ceiling, right?
Exactly. I love it. I'm going to show you how, if you think that way, it'll help you a little bit sometimes. But we don't care about a floor or ceiling. This is it just compares, just take a known series and then make the ratio with the one you're working with. And if the limit comes out to be between those, they do the same thing, period.
Every time.
The direct comparison test is exactly as so desperately direct. It just says,